Okay, so that was the example that we did, and that was for a gas phase in a batch reactor. That we wanted to find, for example, the time that you achieve certain conversion. In that case, was 90% conversion. We did the first two steps. And now the third step is the stoichiometry, obviously. The stoichiometry is because we don't have any change is gas phase, but is in a batch reactor. Batch reactor means that your volume is constant. So therefore, you are going to use the constant volume relationship between concentration and conversion. So CA would be CA naught 1 minus X. And if you put it in the rate law, because our rate law was KCA squared, would be K CA0 squared 1 minus X squared. 1 minus X squared. And then you combine those. The fourth step was combine those, the stoichiometry, rate law, and the design equation. So if you do so, you're going to get dx dt would be kCa0 squared 1 minus x squared Ca0, and that would be kCa0 1 minus x squared. If you go through the integration, would be dx over 1 minus x squared would be equal to k Ca0 dt, and then your integration would be 1 minus x 0x k Ca0 t, and then would be 1 minus x 1 minus 1 would be k Ca0 t, and then you put the parameters, which is x is 0.9, k is 0.29 liter per mole second, and Ca0 is 0.2 molar or mole per liter. So if you put these parameters in this equation, you are going to find t is equal to 155 seconds in order to achieve 90% with that condition. I'm going to do another batch reactor, but this time we just find the equation in general rather than putting the numbers. So the same thing with the gas phase, and then see how does it. Okay, so how does it fit into the equation? Again, we are going to discuss batch reactor, and so it would be a gas phase, So, for example, like 2A gives B plus C. And we want to find the expression for the time, to achieve conversion X. So the same step, very similar to previous example. Step 1. So you write the design equation, which is dx dt is equal to minus RA CA0. And then we have the step 2. Step 2, we have the rate law. Our rate law is the elementary type rate law, which is minus RA is K CA squared. Okay. The third step is stoichiometry. The stoichiometry for this case, which is again is a gas phase, but we are dealing with a constant volume because it is in a batch reactor and doesn't say that the volume of the batch is changing. So we consider like for the stoichiometry CA C naught for the stoichiometry, we consider CA is equal CA0 1 minus X. And then we combine these T in this equation. So we come to this dx dt is going to be K CA0 squared. CA0 is a squared. There would be another CA0 in the numerator that cancels out. So it would be KCA0 1 minus X squared. And then you evaluate the integration. So it would be dt if you bring dt in one side and bring the other ones in another side, it would be dt from 0 to t equal to 1 k CA0 dx 1 minus X squared. And if you do so, then your final time to get the X% conversion would be 1 k CA0 X 1 minus X. If you do similar things for a first order reaction, maybe do it as an exercise. Similarly, with first order reaction, so this was the second order. If you would be an easier integration event with first order reaction. So you will get TR to be 1K ln 1 minus X. So now I'm going to do another example, but in the second example, I'm going to just use the Cstr, a mixed flow reactor, but with liquid phase, which is an easier case. And then when we finish this one, I'm going to just give you another example that we have two CSTR in series and see how does that one works. These are, although it seems different examples, but all it changes depending on the condition of the problem is either liquid or gas, or it changes the design equation. They are all the same. Even with the multiple CSTR, you have from previous chapters you have a certain design equation. So all you need to do just plug in the right equation and then combine and do the integration. So as I mentioned in previous lectures, combining and taking the integration is just when you want to solve the integral by hand. If you use the solver like Polymath or ComSolver or other things, you don't need to combine this equation because the software does for you. Or if you want to use any code to do the integration, then also you need, like MATLAB, you need to find your final version of the equation and then use one of the integral schemes like Simpson's or 3/8 law or 1/3 polynomial law, so just to take the integration. Right? Seems very easy, huh? Yes? Okay, as I mentioned, let's do another example now. So that would be, we are going to have a continuous stirred tank reactor. Acronym is CSTR. Some book says mixed flow, again, the same idea. And we have liquid phase. Liquid phase. Okay, so let's assume we have schematically something like that. And we have a mixer inside. We have Hefe nut coming to the reactor. And let's assume a first order reaction. First order reaction. And find the exit concentration. Exit concentration for this reactor. So what would be the exit concentration for the reactor? Would be the same concentration in the reactor because the mixed reactor, correct? But just keep in mind, if you, not your book, there are more advanced books that shows how to deal with this one with non-ideal condition. This is the ideal condition. We consider that all the molecules everywhere in the reactor are acting the same things. But it's not the case. So the molecules here, or here, they tend to stay more into the reactor than molecules, let's say, in the center, so which go like this. So in reality, the molecules there is a function called the residence time distribution. And this is not part of your subject. So what it is, so it shows how the distribution of the particles are in the system, and they call it E as a function of T. So then, in reality, you need to consider such function into the system, and then apply some models, like segregated models or other models, in order to do the conversion, determination, or concentration calculations. So it would be another 1-2 steps to consider those changes, right? But this is good news. This is for advanced courses, so you don't need to know this system. Just to give you some idea how does it work. Okay, so step 1. What was step 1? Was the design equation. So remember from chapter 1 and 2 that design equation is an algebraic equation. Again, this is the easy part about the CSTR. You don't deal with the integration, it's the algebraic equation, correct? Is V is equal FA0 X minus RA. Again, we had, just because we are dealing with the molar flow rate, so just get your attention to equation. We have FA0 is V0 CA0, and then if you remember, we discussed the tau, space-time, and then that was V, capital V over V0. So you can convert this equation to include the tau rather than like x. And the reason is that sometimes you have the tau as a design equation. Like they might give you the tau. So therefore you need to convert the equation as a tau. So nothing fancy. Basically you replace for example, the x to the tau with additional terminology that is there. So we don't do anything extra here. So basically your tau would be V over V naught, and that would be CA0 X minus RA. So what we did here, so you can see this equation. If you divide by V0, that gives you tau, and FA0 over V0 gives us CA0. So basically, this equation is this equation, correct? So what you have done, you have divided both sides by V0 to get the tau out of this equation, right? Correct? Yes? Okay. So I'm going to flip the page to finish. Okay, so step 2 was the step 2 is the first order reaction minus RA is KCA. Step 3 is the stoichiometry. Liquid phase CA is CA0 1 minus X. Step 4, combine. So your tau would be 1K X over 1 minus X. Or you can single out X from this equation. Find X would be K tau over 1 plus K tau. Now if you apply CA0 1 minus X to this equation, you can find CA from this equation. CA would be CA0 1 plus K tau. If you plot the X versus K tau, it gives you something like that. So the k tau is a number that I'm going to introduce in a moment. We call it Dampf-Kochler number. There is a number, is Dampf-Kochler number is a non-dimensional number that shows the ratio of the reaction to the mass transfer. Basically, this is the vertical axis is a representation of the volume of the reactor. The volume. T has to do with the volume, right? Is volume over V naught. So it means that, I mean, this, I drew it just like that, but if you put the numbers there, so you're going to get something like that as well. It means that after certain k tau, if you increase the volume of the reactor, you are not getting a lot from the conversion. So as a design equation, so for example, you might want to just work in this area. That gives you the maximum conversion. And if you go beyond certain k tau, you are not going to gain a lot on the conversion side. Right? So this is basically shows how the volume is influencing the conversion of the reactor. So adding the volume to some extent might increase the conversion, but it levels off at some points. If you do a second order liquid reaction in Cstr, if you do a second order liquid reaction in Cstr. So the previous example was first order. You just change it to the second order. So all you need to do just get this ones replaced by kCa squared, and then take the integration. I'm going to just write quickly what you need to do. Basically, your design equation is Fa0x minus Ra. Your rate law is minus Ra. The second stage is kCa squared. Your stoichiometry is Ca naught minus x. And then you combine those equations. So you will find V is going to be equal to Fa0 x k Ca squared rather than kCa. So you need to solve this one if you want to find the x or conversion. So that would be an easy solution, but I'm going to just include this one so just for you, just as an exercise. Your V would be V0 as Ca0x k Ca0 squared 1 minus x squared. If you divide by V0 both sides, this V0 cancels out, and V over V0 gives you tau. So basically your tau would be x divided by k Ca0 1 minus x squared. So what we did here, you divide by V0 both sides. So then is a polynomial that you need to solve it, and your x would be 1 plus 2 tau k Ca0, and there is plus minus sign, but you choose the negative sign, because if you choose the other one, then your x goes out of the range. So your x should be somewhere between 0 and 1, right? So this plus minus sign you decide depending on the condition of your problem. So it's 1 plus 2 tau k Ca0 squared and minus 2 tau k Ca0 squared, and then that would be divided by 2 tau k Ca0. Okay, so I'm going to flip the page. So if you do this once, there is one more step that gives you simplify this equation, and this time your book has shown this one as a function of the Kohler number, and that's has some significance that I'm gonna just show you what is the use of this non-dimensional number. Okay, so then if you continue with that previous equation, so it's going to be your x is going to be 1 plus 2 tau k Ca0 over 2 tau k Ca0 minus 1 plus 4 tau k Ca0. That's your conversion, and this one, as I mentioned, is defined as a Kohler number, is 1 plus 2 dA 2 minus 1 plus 4 dA. dA is Kohler number over dA. So where dA is Kohler number. It's the name of a German chemist that came up with this number, and in this case, for the second order reaction, what is first order or second order? So that was a Cstr, second order. So this is tau k Ca0. That's the definition of that Kohler number. I'm going to give you a brief description of what the Kohler number is, that you have some appreciation of this non-dimensional number. So non-dimensional numbers play a significant role in engineering science. So you have had these numbers in other courses, like for example in fluid mechanics, you have had what's the main non-dimensional number? Reynolds number, rho ud over mu, and that has some. It's not like like non-dimensional definition. It has some significant physical demonstration. Like for example, it shows the ratio of the non-viscous forces over the viscous forces, or the Reynolds number. So in heat transfer, you have what number in addition to Reynolds? Prandtl number, PR, right? Help me just to remember what was it? Cp mu over K, right? Prandtl Cp mu over K, right? And in mass transfer, we have maybe, I don't know, we are dealing with oh, you have 4 or 5 course, right? 4 or 5. So a Schmidt number, right? The Schmidt number is the ratio of kinematic viscosity over diffusivity, right? Correct? Right? Is mu over d. So they have a meaning. They define a ratio of some force or some reaction or some transport phenomena to other ones that can tell you, like for example, where you locate. For Reynolds number, like the higher the number is, that shows that you are more towards the being turbulence, because the non-viscous forces, the non-viscous forces are dominant than the viscous forces. So for this number, which of course you don't hear that much because it's more specific in reaction, shows a ratio of reaction to the mass transfer. This is the definition of that. I'm going to just put a few words on the board so you can understand what this number is. So it is a dimensionless number. Dimensionless number. So gives it gives a quick estimate. Quick estimate of the degree of conversion in a continuous flow reactor. So this is defined for continuous flow reactor. So if you write it down, so dA would be minus RA0V over FA0, which is the rate of reaction at entrance over entering flow rate of A. Entering flow rate of A. For a first order reaction, so this is going to be the Dampf-Poehler number is going to be K Ca0 V over V0 Ca0, which gives you tau over K. For a second order, reaction, Dampf-Poehler number is going to be K Ca0 squared V over V0 Ca, and that would be tau K Ca0. So in general, there are again, if you go depths into this topic, into this number, there are two type of Dampf-Poehler numbers. This is Dampf-Poehler number 1. So in general, the Dampf-Poehler, which is Dampf-Poehler number 1, is going to be K Ca0 n minus 1 tau. This is in a general case. So a rule of thumb, So if your if the application in the reaction engineering, if your damp folder number is smaller than 0.1, your X or conversion would be less than 10%. And if your damp folder number is more than 10, this is again rule of thumb, so just approximation. If your damp folder number is more than 10, means that your conversion most likely would be more than 90%. And between those numbers, your conversion falls between 10 and 90%. Is it clear? Is it understandable? Right? Nothing fancy, just some definition. Otherwise, the rest is just solving that ODE. Right? So let's do another example. This time we are going to put the CSTRs in series, just to find out how this one works. So I will start the problem, then we go. Then if there is something left, we do it in the next lecture. So that's we start with 2 reactors CSTR, and then we generalize it for more than 2, can be 3, 4, 5, n reactors. Because as long as these reactors have the same volume and the same condition, you can put the equations together. If there is different in terms of the size of the reactor, then you have to do it one by one, consider one by one. But you will see that at the end of the day, you are going to have a very general formula that applies for n, that n can be any number of reactors in series. Okay, so the topic is CSTRs in series. Let's start with a simple case, which is like 2 CSTR with the same size. Same size. So we have Ca naught. We have Ca naught comes to this reactor, and then we have from the bottom we have Ca1 and X1 going out of the reactor, and then this is going to be fed to the second reactor, and then at the bottom of this one we are going to have Ca2 and X2, and so we consider the rate of reaction is minus RA1 here minus RA2 here. And for just to make it first simpler, we deal with the liquid phase. And after all, CSTRs are more used for liquid phase rather than the gas phase. When you go to the gas phase, most of the time, we use the tubular reactor, but we consider the liquid phase. We consider a first order reaction, again, just to make things easier, first order reaction, and then we generalize this one. we generalize the number of reactor, we generalize this, this order of reaction. First order reaction, and no change in volumetric flow rate. In volumetric flow rate, that basically what it does means you can imply this once from this being the liquid. So it means that your V is equal to V naught. So you are not changing the volume, which is obvious when you are dealing with the liquid phase. Sometimes if you have like how you can be liquid phase, and this changes that for some reasons the volume through the second reactor because of the change of like resistance and other things will be changed, although it's a liquid phase, but these are when you are dealing with the pressure drop. Again, in the context of your course, only we consider pressure drop for the packed reactor. We just don't consider the pressure drop here. So, I mean, between the two reactors, so in reality, you're going to have like half a meter pipe, and that's not going to have a pressure drop fully. Pressure drop, remember from fluid mechanics, is when you have a long piping, right? Or you have a lot of bends and fluid response. So we don't consider the pressure drop here. So the pressure drop that we consider, and then I will discuss this in 2 lectures, would be when you are dealing with the packed reactor. You have the catalyst in your reaction, in your reactor, and then the flow goes to the catalyst is dropped.